thin layers of microporous crystalline materials such as zeolites, MOFs, and ZIFs are used as membrane constructs for a variety of mixture separations. Most commonly, the mixture separations across microporous membranes are carried out under steady state conditions. In a number of experimental studies, however, the transient mixture permeation of various gas molecules have been investigated. As an example, I present here the component fluxes for methane and normal butane across a MFI zeolite membrane that consists of a set of intersecting channels. These are the straight channels, these are the zigzag channels, and these are the intersection points. MFI stands for mobile 5. The channel dimensions are about 5.5 angstrom. What is remarkable about these experimental studies reported by Geuss is that during transient permeation, methane exhibits an overshoot in its component flux before it reduces in value to the steady state flux. And at steady state, the mixture permeation is selective to normal butane that has the higher adsorption strength. However, during the early transients, the permeation selectivity is in favor of methane that has a significantly lower adsorption strength than normal butane. We asked this question, why is this overshoot? What causes it? And in this presentation, I shall address this question. As background material, please also watch the videos on steady state membrane selectivity versus permeance. There was another video on tutorial on membrane permeation. There are other video presentations on transient overshoots within spherical particles and uphill diffusion within crystalline materials. These are all available on my YouTube channel. I shall proceed with the modeling of transient membrane permeation in order to provide a fundamental understanding of the reasons behind the observed overshoot. This is a schematic of a membrane construct. The microporous layer has a thickness of delta. The upstream compartment has partial pressures P1 and P2 of the gas molecules 1 and 2. And the downstream partial pressures are P1 delta and P2 delta. The upstream face of the membrane is in thermodynamic equilibrium with the partial pressures in the upstream compartment. The downstream face of the membrane is in thermodynamic equilibrium with the partial pressures P1 delta and P2 delta in the gas phase in the downstream compartment. The molar loadings Q1 and Q2 at the upstream phase, Q1 delta and Q2 delta at the downstream phase can be determined from the mixture adsorption equilibrium. Typically, we use the ideal adsorbed solution theory to determine the component loadings in the upstream phase and the downstream phase of the membrane layer. The transient development of loadings within the membrane layer is described by this partial differential equation, where Z is the direction coordinate along the membrane thickness. Ni represents the fluxes of components 1 and 2. Using the Maxwell-Stefan diffusion model, and the details of the Maxwell-Stefan diffusion model can be obtained or in my publications. See also my video presentation, Diffusion in Ordered Crystalline Microporous Materials, on my YouTube channel. These these transmembrane fluxes are expressed in terms of the molar gradients in the molar loadings by this expression, which is derived from the Maxwell-Stefan diffusion theory. Written in matrix notation, we have a scalar multiplying factor. Rho is the mass density of the membrane. We have a matrix of diffusivities. These diffusivities, d sub 1 and d sub 2, represent the Maxwell-Stefan diffusivities for molecule wall collisions. In addition, in general, we need to take account of correlations between the mobilities of species 1 and 2. The correlation effects or the slowing down effects are reflected in these ratios, d1 divided by d12 and d2 divided by d12. d12 is the exchange coefficient between species 1 and 2 and may be regarded as representing the correlations in the molecular jumps. If the correlation effects are ignored, these off-diagonal elements reduce to 0. This also reduces to 0, and we have a diagonal matrix. In general, of course, we need to take correlation effects into account, as we shall explain in the subsequent slides. Besides the matrix of diffusivities here, we have a matrix of thermodynamic factors, gamma 11, gamma 12, gamma 21, and gamma 22. These can be determined from mixture adsorption equilibrium. They are also, in general, strongly coupled. In other words, the cross coefficients gamma 12 and gamma 21 have significant non-zero elements. And we shall show that it is indeed the thermodynamic coupling effects engendered by gamma 12 and gamma 21 that causes the transient overshoots. The set of partial differential equations here with this flux expressions need to be solved numerically by appropriate discretization of the membrane layer. Further details of the discretization procedure for calculation of the fluxes are discussed in my publications. We proceed now with examining the experimental data and comparing the experimental data on transient membrane permeation with the simulations using the Maxwell-Stefan diffusion model. We start with analyzing the experimental data of Geuss, published in Microporous Materials in 1993, showing the experimental data on transient permeation of mixtures of methane and normal butane across an MFI zeolite membrane. The simulation results for transient membrane permeation using the Maxwell-Stefan diffusion equations are presented on the right-hand side. 3 different models are used for determining the fluxes, and they are all compared in this graph, which plots the normalized flux, where the normalized flux is defined as the molar flux divided by rho, the mass density of the membrane, the molar loadings at the upstream face of the membrane, the Maxwell-Stefan diffusivity for molecule wall interactions divided by the membrane thickness. This is the normalized flux of methane. This is the normalized flux of normal butane, and this is the square root of time in square root of the time in minutes. The 3 different models are shown here. The blue line shows a model in which thermodynamic coupling effects are included, but the correlations are considered to be negligible. The red line shows the simulation data for the model that includes thermodynamic coupling and also the correlations or slowing down effects. The dashed line represents a model in which both thermodynamic coupling effects and correlations are ignored. We note the models in which thermodynamic coupling is included, the flux of methane shows an overshoot. And if thermodynamic coupling effects are ignored, the overshoot disappears. The inescapable conclusion is that the overshoot in the methane flux is engendered by thermodynamic coupling effects. Details are available in my publication from 2016. We continue with our discussions on methane normal butane permeation across an MFI membrane and the simulation results for the transient development of the membrane loading in the along the thickness of the membrane are shown here. The red line shows the methane loading at a time 0.4 seconds. This is 3.4 seconds, 8.4 seconds, and this is 400 seconds. This is practically close to the steady state conditions. We note that the methane loading overshoots the value at the upstream phase to a significant extent during early transients, and this is in line with the overshoot in the flux of methane that is observed during early transients. In this graph, which is in 3D space, we showed the component loadings of both methane and normal butane. There is no overshoot or undershoot in the loading of normal butane as it develops from the upstream phase to the downstream phase. Details are available in my 2016 publication. In a paper published in Industrial Engineering Chemistry Research in 2000, Matsu Fuji published experimental data on transient permeation of mixtures of normal hexane and 2-methylpentane across an MFI membrane, shown here. We note that during the early transients, normal hexane shows a a pronounced overshoot in its flux. And this value of the flux reduces to the steady state value at long times. The same holds for permeation of mixtures of normal hexane and 2,3-dimethylbutane across an MFI membrane. The modeling of these experiments was carried out and published in this paper, and I will discuss the simulation results in the subsequent slide. This graph shows the simulation of the experiments for permeation of normal hexane and 2-methylpentane across an MFI membrane. Two different models are considered. The continuous lines are the models in which thermodynamic coupling effects are duly accounted for, and the dashed lines are the simulations in which thermodynamic coupling effects are considered to be negligible. If thermodynamic coupling effects are duly accounted for, we observe a transient overshoot in the flux of normal hexane. And this is in accordance with the experimental data of Matsufuji. If thermodynamic coupling effects are ignored, no such overshoot is observed. The same set of data is plotted in 3D space in this right figure. Details again in my 2016 publication. The graph here on the left-hand side shows experimental data reported by Barker in his PhD dissertation in 1999 for transient permeation of hydrogen and normal butane across an MFI zeolite membrane. Remarkably, we see a very pronounced overshoot in the flux of hydrogen during early transients. In other words, the membrane is selective to hydrogen during the early stages of the transients, but at steady state, the membrane is strongly selective to normal butane. So we have selectivity reversal as time progresses. The simulation of these experiments are shown in this right figure using two different models. The red line shows the simulations in which thermodynamic coupling effects are duly accounted for, and this shows a strong and pronounced overshoot in the flux of hydrogen as observed in the Barker experiments. If thermodynamic coupling effects are ignored, this is shown by the dashed lines, then no overshoot in the hydrogen flux is anticipated. Experimental data on the permeation of mixtures of xylenes have been reported by Matsufuji in General Membrane Science in the year 2000. I show here two sets of experiments for 50-50 paraxylene metaxylene mixtures. This shows a pronounced overshoot in the flux of paraxylene during early transients, and these are the experimental data for permeation of a ternary mixture of paraxylene, metaxylene, and orthoxylene. Again, we see a pronounced overshoot in the flux of the paraxylene gas molecule during early transients. It is important to note that ortho and metaxylene prefer to locate at the channel intersections, whereas paraxylene is free to locate anywhere along the channels of MFI. The simulation of Paraxylene metaxylene mixtures were carried out and will be presented in the following slide. Here are the simulation results for permeation of paraxylene metaxylene mixtures across an MFI membrane. Two types of simulations were carried out. The continuous lines show the simulations in which thermodynamic coupling effects are duly accounted for. The dashed lines are the simulations in which thermodynamic coupling effects are considered to be negligible. Taking due account of thermodynamic coupling, we observe that the flux of paraxylene exhibits a pronounced overshoot in line with the experimental results of Matsufuji shown in the foregoing slide. The same set of simulation data are plotted in 3D space in this right figure. The details are available in my 2016 publication. Here are simulation results for permeation of normal butane, isobutane mixtures across an MFI membrane. The continuous lines are the simulations in which thermodynamic coupling effects are duly accounted for. The dashed lines are simulations where thermodynamic coupling effects are ignored. And just as in the previous slides, inclusion of thermodynamic coupling effects results in a transient overshoot in the flux of the more mobile normal butane molecule, whereas this overshoot disappears when thermodynamic coupling effects are ignored. These simulation data are plotted in 3D space on the right-hand side, and both these diagrams are taken from my 2016 publication on the transient overshoots in binary mixture diffusion. The previous slides all considered mixture permeation across MFI membranes, so let us now turn to permeation of propane mixtures across ZIF-8 membrane. The ZIF-8 membrane is made up of ZIF-8 is made up of a structure that consists of cages separated by windows, and the crystallographic dimension of these windows is about 3.3 angstroms. The windows are flexible, that allows the molecules that are larger in size than 3.3 to pass through. Due to the subtle differences in bond lengths and bond angles, the diffusion of propene is about 2 orders of magnitude higher than the diffusivity of propane. The molecules jump one at a time across the windows, and the intercage jumps are uncorrelated. So correlation effects can be ignored, and all coupling in the permeation fluxes is engendered by thermodynamic correction factors. Two types of simulations were conducted. The continuous lines are the simulations that include thermodynamic coupling, and we note a significant overshoot in the flux of the more mobile propene, whereas the dashed lines are the simulations in which thermodynamic coupling is considered to be negligible, and no overshoot in the propene flux is observed. The details are available in my 2016 publication in Physical Chemistry, Chemical Physics Journal. There is no direct experimental evidence of these overshoots, but experiments, if conducted, will confirm these transient overshoots. The simulation of water ethanol per-evaporation across a DDR membrane is presented in this graph here, and this shows that during transient permeation, the water flux shows a pronounced overshoot before it reduces in value to the steady state value. If we ignore thermodynamic coupling, no overshoot in the water flux is detected. It's interesting to note that during early transients, the permeation selectivity is strongly in favor of water. DDR consists of cages separated by windows, and the window aperture is approximately 4 angstrom in size. This graph shows the development in the water loading across the DDR membrane, and during early transients we note that the component loadings of water within the membrane layer is significantly higher than the loading at the upstream face of the membrane, and this is in conformity with the overshoot in the flux of water during early transients. Precisely analogous results are obtained for water ethanol per evaporation across LTA4A membrane. During early transients, the water flux shows a pronounced overshoot. These are the simulations that include thermodynamic coupling. If thermodynamic coupling is ignored, no overshoot in the water flux is realized. The simulation data for the development of the water loading within the LTA4A membrane layer are shown here. During early transients, the water loading exhibits an overshoot. The values at these maxima are significantly higher than the values at the upstream face of the membrane. Thus, the overshoot in the water loading is in conformity with the overshoot in the water flux for membrane permeation across the 4A membrane. Using a wide variety of examples for permeation across MFI membranes, ZIF-8 membranes, DDR membrane, and LTA4A membranes, we have demonstrated that for mixture permeation under transient conditions, the more mobile component exhibits a pronounced overshoot, and this overshoot is ascribable due to thermodynamic coupling. And if we ignore thermodynamic coupling, no overshoots are realized. If you ignore thermodynamic coupling, the steady state fluxes are also not properly modeled. So the major takeaway from this presentation is summarized as follows: ignore thermodynamic coupling at your own peril.